Hello everyone, my name is Elise, and today I'm going to talk to you about what it means to be a selective reliability engineer. Before I get into that though, let's build a system together. We'll start with a simple service that accepts image uploads and serves them on demand. We need at least one application server and some place to keep the images. We want to monitor it too, of course. Let's set a latency target of, say, half a second. You can always tighten that up later. Oh, and let's make sure everyone can see our cats. We need a globally consistent store. So let's think about how we might implement this. Oh, I know. We'll write our application in C so it's really fast, use the local file system to store images, and only run a single copy, and not write a single bug. That should meet all those requirements. Okay, maybe that's not exactly the design we would choose today. I have to admit the server under my desk isn't that reliable, and it probably couldn't handle that much load. So what about a more modern design? We could write our application in something a bit safer than C, say Go or Python. We can make it stateless so that it can handle a lot more load and scale automatically. We'll still need somewhere to run it and to store our data, so maybe we can leverage our cloud offerings. We can use their load balancer, relational database, and blob storage. That should also meet the requirements that I laid out. A major part of being an SRE is making decisions. We're constantly evaluating trade-offs between risk, effort, and value. We designed two systems we could build, so how do we choose between them? Ideally, we would make the best choice, but how do we do that? Is there even a best decision in the first place? What is the one true way to design a system? Let's look at those two systems we designed a little bit closer. One big change we made in the second one is we started to leverage best practices. Following these design guidelines let us benefit from the experience of SREs in the past. Unfortunately, best practices don't stay the best forever, and they don't work in all situations. So what should we focus on? What did our designs have in common? Well, we designed them by looking at the technical constraints we had. Neither design made a single reference to the users of our system. These systems accept uploads and serve images, but from who and to who? Well, from humans. As we design our systems, we select what is important and what isn't. It's in making these selections that our true role becomes apparent. We are doing selective reliability engineering. System design is an implementation detail of how we fulfill our role, not the role itself. Our role is to improve the reliability of human systems at the end of the day. Speaking of humans interacting with humans, let's take a road trip together. I've been thinking a lot about the phrase single source of truth. It's one of those mythical best practices that we talked about earlier, something to keep in mind as we design a system. Every interface that our system interacts with is a potential source of data. That's databases, external providers, and other local services. Ideally, only one system handles the mutation and storage of a single data type. So back to the image system we designed earlier. Suppose we added a subscription service for higher quality cat pictures, and also enabled you to send a physical copy of the picture to your friend. If we then support multiple payment providers, it would make sense for us to dedicate a service just to financial transactions instead of duplicating that logic and risk synchronization issues. This simplification lets us consider the system at a higher level and not worry about everything, everywhere, all at once. Ultimately, for every type of data, it's best practice to ensure that there is a single source of truth. But there isn't. There is no single source of truth. Okay, let's put that oblivion spiral aside and start that road trip I was talking about. When we consider how we should optimally build our systems, there's always surrounding context. Designing a system requires selecting a scope and a scale to work within. There's a slight difference between a microservice that gets a single request an hour and a highly available distributed lock service. The bulk of a design doc often focuses on system-level complexities like data representation and semantics. At this level, we can ask questions about data types, time zones, precision, and data synchronization. We can consider if we really need microsecond granularity on our monthly reports. We can consider if we should store times as the number of seconds since the last ice age. We might also choose one algorithm over another, depending on the scale and accuracy that we need. Not considering these questions can risk system and data integrity. While ignoring time zones may not significantly degrade the user experience of our image service, it would be disastrous for a system that schedules meetings. Our design docs also consider operational complexities. We don't just design a system to store data now, we design it to continually assist both operators and users over time. At this level, we can ask for details around SLAs, metrics, and incident runbooks. We can decide if an hour response time results in a missed SLA, how detailed our observability data really needs to be, and what our plan is to recover from outages. Not asking these questions means our system might be more prone to downtime or increase the time needed for incident resolution. As an organization grows, our design docs begin to grow with it. They start to detail systems of systems and their interrelationships. Each system we create is part of the interpersonal processes that we use to develop software in the first place. It's this holistic level that lets us consider a design doc for the organization as a whole. The questions asked at this level are more about process, product, and policy. When we don't ask these questions, this can leave us stuck with systems that we've grown out of, or blind to opportunities that will help us make better trade-offs. Although our day-to-day decisions might not always be this broad, each of the selections that we make in the smaller case influence the larger picture. And with this more holistic view, we've hit our philosophy detour. Let's look at the phrase single source of truth a little more closely. We're engineers, so let's start backwards. What exactly is truth? In one sense, truth is a claim about knowledge. Epistemology explores knowledge, how we obtain it, and how we can know that something is true. Two people can see this image and perceive the dancer spinning in totally opposite directions. So truth must depend on the observer. Also, that's not a dancer, it's only the representation of one. Truth might be orthogonal to the question we're actually asking. In another sense, truth is a claim about assumptions. Mathematical logic defines an axiom as a premise that we take to be true. We can then use those axioms to define a formal system. Depending on the axioms you choose, we can say that 1 + 1 = 2, or 1 + 1 = 10. And so truth must depend on our surrounding assumptions. In a third sense, truth is a claim about accuracy, precision, and semantics. The kilogram used to be measured by comparison to a physical object, the International Prototype Kilogram. Now we define it mathematically by physical constants. There's always uncertainty and reliability in the values that we select for our truth, even at the space level. So all of this seems rather abstract. Let's try to head back to the overlook and look at some concrete cases to ground us. Suppose a user requests a cat picture from the system that we built earlier, but they don't have access to it. Should we return a 403 forbidden error or a 404 not found? Well, the truth would be to return a 403. We'd like our system to behave truthfully, right? But if we do that, we end up revealing a resource's existence, which can have security or even legal implications. It might be better to actually lie instead. As microservices grow increasingly complex, we also need to handle timing and synchronization failures. Data can be delayed for an arbitrary amount of time or not arrive at all. If this failure mode is not handled properly, then the system might actually end up misleading our users in a way we don't want. So how can we avoid telling the truth when we should lie, and lie when we should tell the truth? Avoid lying when we should tell the truth. Here's a case where the best practices can help us a lot. We write code and we test edge cases. We capacity plan and we gather metrics. These production practices help us figure out if we've introduced issues that we've already considered. We already know that this helps us with the technical parts of the code we write, But we also need to expand our insights to the non-technical layers. Ultimately, the uncertainty of truth and the complexity of design points to what we're really doing when we design a system, selecting the best outcome for ourselves, our users, and our company. Our selections include technical decisions about data modeling and non-technical decisions about policy. In the 1980s, a series of locally optimal process decisions and design trade-offs enabled a chemotherapy machine to kill patients with excess radiation. Some of the design decisions that that company made actually made sense in isolation. They reused some seemingly reliable software to enable faster development velocity, and they removed some redundant systems to reduce the cost of the machine. But together, those decisions ended up costing human lives. Although we aren't all working on radiation therapy machines, we are making design decisions that help some people and hurt others. Two-factor authentication requirements, CAPTCHAs, and device attestations are all design decisions that intentionally reduce the accessibility of our systems. Users can be locked out of their accounts with no recourse, especially as AI starts to take over a customer support role. I'm not here to tell you that these selections are right or wrong. I just think that these human edge cases are worth considering. So, what is our role as SREs? Well, as I said, it's to perform as a selective reliability engineer. As SREs, we're always working with other people, engineers, our coworkers, our business partners, and of course, our users. We're keeping the system reliable for, well, people at the end of the day. Every day we build a system, we're building tools of leverage. In making our selections, we multiply the effectiveness of people and reinforce the behaviors that our systems incentivize. We choose based on personal experience, and we optimize what we look to optimize. I suggest we select for empathy and include it in our design requirements. Our users create their own workflows with our system, and it's up to us to keep them working. Our teammates want to have friendly design discussions, not heated fights over technical minutia. Ultimately, the truth is that we determine what the truth is. Our experience of the world is shaped by our own values and beliefs. We can choose to believe that the numbers representing humans are not just numbers. Keeping humans in mind helps ground us in the non-technical part of systems engineering. Each system we build affects the design of the global system, life, and all the people around you. Your choices impact the system of people on your local team, your whole organization, and your customers. Best practices are guidance, not dogma. You are responsible for the decisions you make and for the happiness of those around you. So let's select for empathy in our designs. Ultimately, we're here for each other, not for the machines. Thank you.